Hello everyone. Let's analyze. So what is the integral from 0 to 1 of 1 over the square root of x? Is it anything? If we consider it in the standard case of our Riemann integration, we might partition the interval from 0 to 1, except that 0, which must be a partition point, is not in the domain of 1 over the square root of x. In other words, 1 over the square root of x is not defined there. Even if I were to define my function there, let's say to be 0, the supremum over the first non-empty partition is always going to be unbounded or infinite. There's no way then that the infimum of the upper sums, right? Remember, the upper sums is the sum of rectangles whose heights are the supremums at the partition. That's ever going to be finite and can therefore never equal the lower sums, which for this function would be finite. However, if you already did this integral in your notes or in your head, you might think, yeah, but I could still compute that. Well, how do we make sense of this? Let's discuss it. So today we're going to talk about improper integrals. But first, let me say a word about, well, quirky integrals. Let f map A to R. A is a subset of R. Notice how already we've differentiated a little bit from how we define functions when we talked about Riemann integration. For Riemann integration, we specifically talked about domains of functions being closed intervals. A is bounded. In other words, it's contained inside some closed interval. Then I can extend this function to this domain in a way that retains whatever area under the curve for x and a, if that can be defined. So let f tilde of x equal, well, f of x, if x is in A, 0 if x is not in A. Then if f tilde is integrable, on the closed interval a to b, we have the integral over a of f of x dx is equal, well, to that integral. And this makes sense because even though we're extending a to a closed interval, which allows us to bring into play the partitions of upper and lower sums, we're not adding anything to the area under the curve, because if x is not in the domain of f, right, then we have a area under the curve of 0. So we could think of this as our first definition or extension of the standard Riemann integration. Now, the two questions we're going to concern ourselves with today: what if A is unbounded? Question 2, what if F is unbounded? Consider the picture we saw at the beginning of this lecture. In this case, the integrand is unbounded. On the interval that is open on the left side. This would be an example of what we want to ask for question 2. Or consider this example. Here, the domain is unbounded. So this is an example of the kind of integral we want to investigate, suggested by our first question. So for the first definition of how we're going to extend our definition of integration, we're going to define what it means to be integrable on a unbounded domain. Let f map A to R, and let f be non-negative for all x in A, which, while unbounded, is still in R. Define f tilde in the manner that we discussed. It equals f of x if x is in A and 0 otherwise. If the limit as A goes to infinity of the proper integral f tilde of x dx this is shorthand to say that this limit exists and is finite. All right, so when I say a limit is less than infinity, the suggestion is that it both exists and is finite. Notice that this is necessarily a non-negative number because f, our original function, is assumed to be non-negative. So we have area under a non-negative curve. So if this is true, then f is integrable on its domain A. And specifically, the integral is equal to this limit. Right, so here we're defining, right, what is meant by integrable over unbounded domains. Since our standard Riemann integration definition wasn't sufficient to cover this. Now, a bit of warning. Notice that I required f to be non-negative. Of course, what about generic functions on unbounded domains? Can't they be integrable? Well, yes, they can, and we'll get to those definitions shortly. But for generic f, we cannot simply apply this limit. For example, this integral from negative a to a of x is equal to 0, because this is from 0 to a, the area of a positive triangle, and from 0 to negative a, the negative area of a triangle of the same size. Therefore, I get 0, which remains the same as a goes to infinity. However, it is not right to say that that is 0. Specifically because if the upper limit were to go faster to infinity than this, then we would actually get infinity here. That's why it's crucial that this definition only apply to non-negative functions, so we don't get this cancellation. Now we might ask ourselves, in this definition, the lower limit and the upper limit both race away from 0 at the exact same speed. What if this went to infinity faster? Again, for non-negative functions. What if this were 2a and this were negative a? What if this were negative k and this were k plus 1, and k was natural numbers that I was allowing to go to infinity? If that limit were to exist for positive functions, could I still say that this is true? In other words, what if for a non-negative function this converges to some limit as k goes to infinity? Then does the integral of f on its unbounded domain exist? And the answer is yes. You don't specifically have to enlarge your domain in a symmetric way. In fact, you can enlarge your domain in any way. So that idea is summarized in the following theorem. Suppose that f is non-negative and bounded. And integrable on the closed domain negative a to a for every positive a. Then f is integrable if and only if. Now, when I say f is integrable on this closed interval, I mean that I'm using the f tilde extension, so that even if there are portions of this closed interval not in the domain of f, I just set those parts to 0. If rather than taking a symmetrically growing domain, we just take any growing domain under certain conditions. For a sequence of subsets of R, the subset sequence is growing. Now, what do I mean that the subset sequence is growing? Well, I mean it's getting bigger. What do I mean by it's getting bigger? Well, I mean that every subsequence is contained in the next sequence. And specifically, it is growing without bound. What do I mean that these subsets of R are growing without bound? Well, what I mean is for all of these intervals, that is, for every positive a, there exists a k such that the closed interval is contained in some bk. Then the integral equals the limit as k goes to infinity if it exists. And is finite. So, just to review, we've defined an integral on an unbounded domain by extending our function to all numbers by letting it be 0 outside of its domain, and then taking a limit as the lower and upper limits go off to negative and positive infinity. All this theorem intends to show is that I don't have to enlarge my domain in exactly a symmetric way. I can actually enlarge my domain off to infinity any way I like. And so long as that limit exists, then my function is integrable. That's all that this theorem is saying. For most examples we're going to be dealing with this week, the first definition will suffice. Now what about functions on bounded domains where the function is unbounded? Let's go back to the example that we started with. How can we define the integral from 0 to 1 of 1 over the square root of x if the standard Riemann definition would not give me a value for that integral? Well, let fm be f if f is less than or equal to m and 0 otherwise. This is a way of allowing our function to be bounded. Notice that fm is bounded, and of course it's defined on the same domain, which is also bounded. So for fm, we can actually use the standard Riemann definition of integration. For m equals 2, fm appears this way. It's f of x until f of x gets larger than 2, then it becomes 0. So because fm is a bounded function, right, with only one discontinuity, on the bounded interval 0 to 1, I can compute its integral. In fact, I can compute its integral using just standard Riemann integration. And I would get 2 over 1 over m. So now that actually allows us to give a definition for when a function is integrable on a bounded domain if the function itself is unbounded. So let f of x be greater than or equal to 0 for all x in the domain. Now, notice again, this definition specifically and strictly deals with positive or non-negative functions. Now, if I take the limit as n goes to infinity, and I get a finite limit, then I can say that my function is integrable on the bounded domain, and it's specifically this limit. Because the integral from 0 to 1 of fm is 2 minus 1 over m, that converges to 2 as m goes to infinity, and I get exactly that the integral from 0 to 1 of 1 over the square root of x is 2. So it in fact is defined using this extended definition of integration, what we call a improper integral. Let's take a look at another example. Consider the function 1 over the square root of the absolute value of x. And let's define it on the closed interval -1 to 1, but not at 0. Now, I might write the integral from -1 to 1 of 1 over the square root of x. But of course, what I really mean is the integral over the domain, which is of course the same as the integral of f tilde from -1 to 1, where as before f tilde is f if x is in the domain and 0 otherwise. Oh, that's a typo. That should be x in a. But again, I have a unbounded function but on a bounded domain. I can use my same definition. Let fm be f every time f is less than or equal to m and 0 otherwise. That gives me a bounded function on a bounded domain, and in this case my function is actually continuous except for 2 points. So it's integrable. Fm is integrable under the Riemann sense. And if I were to take that integration of fm, I would get 4 minus 2 over m, which converges to 4 as m goes to infinity, which means the integral of 1 over the square root of x over its domain is 4. So if a function is unbounded, or if the domain of a function is unbounded, we've been able to extend our standard Riemann definition of integration to these types of functions if they satisfy certain conditions and are positive, or rather not negative. But what about generic functions? Can't generic functions that are sometimes negative or positive and negative, can't they exist if they happen to be unbounded in certain parts or if the domain is unbounded? Well, in fact, they can, and we can use our definition of non-negative functions to extend to functions that have both positive and negative parts. Let's consider the positive part, f plus. Right, so f plus is just all the parts of f that are positive and 0 otherwise. Suppose that the integral of f plus exists. And by the way, I have all the tools I need to analyze the integral of f plus because it's a non-negative function. Now let's consider the negative part. Now, of course, the negative part is, well, negative. But if I just turn it upside down, that is, take the negative of the negative part, then that becomes a non-negative function, and I can analyze whether that is integrable. So suppose that the integral of the positive part and the integral of the flipped negative part both exist. If that is true, then, well, the integral of the absolute value exists and is equal to their sum, and the difference of the positive part minus the negative part gives me the integral. That is, the integral of f over a exists. Now you might be tempted here to say, well, can't I just check whether the integral of a of the absolute value of f exists? Well, you actually have to be a bit more careful. Think about, for example, the function that is 1 if x is irrational and -1 if x is irrational. And consider taking the integral of that function from -1 to 1. Hopefully we will see that the f positive and the f minus neither exist. However, the absolute value of that function would just be 1 everywhere. So it's important that we consider the positive part and the negative part separately in order to construct our integral if this and this both exist. So the following theorems simplify our definitions of integration for unbounded domains or unbounded functions when we have continuity. So suppose f maps the interval a to forever to the set of real numbers, f is continuous, and f is non-negative. Then f has an antiderivative, and f is integrable if and only if the limit as x approaches infinity of f of x exists. And if it does, that limit minus f of a equals my unbounded integral. The next theorem is for functions that have discontinuities at one end but are continuous everywhere. The next theorems are for functions that are unbounded at one end of a domain. So for example, if f maps the interval a to b, open on the a side and closed on the b side, if f is continuous and non-negative, then f is integrable if, and only if, the limit as h approaches infinity of a plus h to b of f of x dx exists. Now notice this integral, right, suffers no penalty from applying the standard Riemann definition, because on the closed interval a plus h to b, f is continuous, and because the closed interval a plus h to b is closed and compact, f achieves a minimum and a maximum, meaning that the function is bounded. So we know that this is, by a theorem we proved, Riemann integrable for every positive h. If as h approaches 0, this limit exists, then we can say that the integral from a to b of f of x is equal to this limit. So a couple of examples. Let's give an example first of this theorem. And in fact, we kind of saw one already. Right? This function is not defined on 0, so we can say it's equal to the limit as h approaches 0, 0 plus h to 1. I'm going to rewrite this as x to the negative 1/2 dx, and that equals the limit as h approaches 0, x to the 1/2 times 2 from h to 1, which is the limit as h approaches 0 of 2 minus two times the square root of h, which equals 2 as h approaches 0. So again, this picture looks exactly like the picture we saw animated on the screen, except that instead of h we actually had 1 over m squared, because 1 over m squared was the limit where the function became greater than m. Right? If we apply this function to 1 over m squared, we get m, and for everything less than that, we get greater than m. An example of the first theorem in action is the integral from 0 to infinity of e to the negative x dx. Well, that equals the limit as x approaches infinity of the antiderivative of this, which is negative e to the negative x, minus negative e to the negative 0. This is the limit as x approaches infinity, minus, of course, e to the 0 is 1, so that's a positive 1 minus. Let's write this way. Of course, e to the x, as x approaches infinity, this denominator approaches infinity as well. It approaches infinity really fast, exponentially fast, you might say, and 1 over it approaches 0. So I get 1. That's all for today.